Today's lesson will be on conservation of mechanical energy. First, we have to talk about what a conservative force is. There's two ways of thinking about this. The first version is force is conservative when the work done on a moving object is independent of the path between the object's initial and final positions. Another way of thinking of it, version 2, a force is conservative when it does no work on an object moving around a closed path, starting and finishing at the same point. So let's look at the first version. Let's see if this force is conservative. When the ball moves from this position to this position, or it goes from this position all the way through this path to the same final position, it doesn't really matter the path it took. The change of potential energy would be the same for both of them. So in that case, it's conservative. Another way of looking at it is, if you took this rock and you lifted it straight up, you moved up this path, or you went up these stairs, the change in position would still be the same. So therefore, it was conserved. In other words, it's a fancy way of saying really there's no friction. All right, let's look at the other example. Think of it in terms of a closed path. If you're a roller coaster, if you start up at the top of the first hill, is it any possible way that you'll ever get through the whole ride and back up to the same position without adding energy? And the answer is no, because of friction. But if you were able to get all the way around and back up to the same position at the same speed you took off from, then this would be a conservative force acting on it. Okay? And really what this is saying is, it's a fancy way of saying that the friction was zero. All right, let's look a little bit more at this. An example of a non-conservative force would be obviously the force of friction. And we know that force of friction is equal to force of friction cosine the angle times the distance. And the force would be the force kinetic because it's moving, cosine 180 degrees because it's always in the opposite direction of motion. So by definition, the work of friction is always going to be a non-conservative force. It's always going to be acting in the opposite direction of motion. So no matter how hard you try, friction's always going to be slowing you down. It's going to slow you down going down the hill on the roller coaster, and it's going to slow you down going up the hill on the roller coaster. So work done by kinetic friction is always negative. Thus, it's impossible for the work it does on an object when it moves around a closed path to be zero. The only way we can ever do this is to totally assume that there's no friction, and then there's some built-in error in the problem because we're assuming there's no friction when there actually is. All right, in normal situations, we have both conservative and non-conservative forces acting at the same time. So the work done by the net external force can be written as, here's the work done by the net external force, as work conservative plus work non-conservative. And we know that this work here, due to the work energy theorem, would be equal to change in kinetic energy. So we can actually replace work with change in kinetic energy. Work conservative is things like potential energy, gravitational, or potential energy elastic, because those forces are conserved. And work non-conservative would be like the work due to friction. Okay? So they're all happening at the same time. All right, let's look at this again. Once again, we could say this work is actually equal to the change in kinetic energy, and that's the work energy theorem. We could say the work conservative would be like the change of potential energy gravitational and the change of potential energy elastic. And we could also say that the work non-conservative would be like the force of friction, for example. We could actually solve this for work non-conservative. And therefore we have work non-conservative is equal to the change in kinetic energy plus the change of potential energy plus the change of potential energy elastic. So the two types added together. So we can think of this a little bit differently too. We know that change in kinetic energy is Ke final minus Ke initial, and change in potential energy is potential energy final minus potential energy initial. And I actually only showed one type of potential energy here just to make the calculation easier. So in other words, this P is actually both of them. So we can actually rewrite this as work non-conservative is equal to Ke final plus K PE final minus Ke initial plus PE initial. Or in other words, the work non-conservative would be equal to whatever energy we ended up with compared to whatever energy we started with. All right, this is all seeming a little kind of confusing, but let's just say we started with some initial energy. Let's make it 100 units of energy. And we ended with 80 units of energy. Okay? So what was the work non-conservative? Well, it had to be 20 units of energy. Does that make sense? So you started, say, for example, with 100 units of energy, and you ended it with 80 units of energy. So the work that you lost, or the non-conservative work, or the work due to friction, was 20. If the net work on an object by non-conservative forces is 0, in other words, there's no friction, or we're not adding energy to the system in some other manner, then we could say the energy final is equal to the energy initial. All right, what we alluded to is what's called the principle of the conservation of mechanical energy. The total mechanical energy, E, which is equal to Ke plus P, of an object remains constant as the object moves, provided that the net work done by external non-conservative forces is 0. It's really a fancy way of saying that you're not adding work to the system and there is no friction. All right, so let's look at an example of this. On the top of a hill, as long as we assume there's no friction, we're adding no energy to the system, it starts off with whatever energy it has up here, or 600,000 joules. All that energy at this point of this bobsled happens to be potential energy. But as it goes down the slide and there's no friction, it loses potential and gains kinetic. But the total will always remain the same, 600,000, because of the conservation of mechanical energy. In other words, the energies could change forms, but they'll always add up to the same amount.